Alright, so let's have a look at an analysis for our red puck now. So remember, back to our data, our red puck, we had the puck travelling in a vector of slightly off, going at a vector like that, approximately 51 centimetres per second, and that was 94.2 with the horizontal, so that's making 94.2 degrees, and then it was hit by the other puck and it then travelled off in a direction that was, and again I've really exaggerated, 3.6 degrees, and that was at 40 centimetres per second. So there are our original vectors, that's our u and that's our v. Now this time around again we need to understand that our change in velocity is going to be our final vector, take away the initial vector, and again remember that we can't actually subtract, we add the negative version. So I now have to think about what's the negative version of this. So we're talking about a vector that's going to go in this direction here, so the same distance but in that direction there. So we know that we're going to have that, and then we're going to have this, and we're going to place them together. So I'm going to take this one here and this one here. I think I might draw this one first. So again, there's my final velocity vector, and I'm going to try and draw it a little bit more. There we are, 40 centimetres per second. There we go, sorry about that. And we know that the angle in here is still 3.6 degrees. This one here, it's going down now. Remember, I want to still do it as an addition vector, so I'm actually going to just place it head to tail here. And so it's going to be placed here. Okay. And remember that is still with the horizontal, making 94.2 degrees. It is there. So our vector going from the beginning to the end is going to be in this direction here. So again, this is just giving us an indicative idea of the direction of the vector. If we go back to our calculations from the first task, we should be able to see that our vector addition should really be equal and opposite, and hopefully that's what we're seeing here. So here's our previous calculation, and we discovered that the vector was going up in that direction here, and our second vector analysis is showing us the vector going equal and opposite. So let's see how close we actually get in regards to our data, and this is where we really have to see if we can do some clever calculations. So this time round we need to actually work in trying to find out what our final velocities are. So probably the easiest way to do this is to actually break this down twice into two sets so that we can work in the horizontal and the vertical, because we need it in a coordinate system. So at the end of this we really need to know what angle this is making. So we're after an angle in here that's going to make there. So we have some information that we can use. We know that this is 94.2. and we know that this is 3.6. So we're going to have two trig problems to solve, and I'm sorry about that, but that really is the only way that we can do it. So remembering that this vector here is actually made up of two vectors, one vector that's going to go along here and straight up like that, and that this vector here is also made up of two vectors, one that's going to come straight down like that and across like that. So by drawing that in, we can see that these two vectors here will add together, and this vector here will subtract with this vector here. So that vector is going down and that vector is going up. So I'm going to find the values of those two and sum them together, and I'm going to find the value of that and subtract it from there. So literally what in the end what I'm doing is I'm going to find a triangle. So just moving that line up, and that's the triangle that I need to solve to find that particular vector. So I'm going to redraw that because it's all starting to look a bit messy. Here's the vector. And as I find that data, I'll plug it into here. So remember, this distance from here to here is going to be made up of that one and that one. And this distance from here to here is going to be made up of that distance, subtracting that distance. So I've got a bit of trig to do. Let's solve this triangle first. So remember, that's 3.6 degrees in there. So this is going to be, and remember that's 40 centimetres per second, so that's going to be 40 sine 3.6. And from here to here is going to be 40 cos 3.6. So that gives me that section there. And then I need to solve this triangle here. Now, solving this triangle, we know this angle in here. This angle in here is 94.2, which means we also know that then this angle is in here is probably going to be 4.2. How do I know that? Because if this is making an angle with a 90, if that was straight up, then that little angle in there would be the same as that one in there for the vertical. So I know that's 4.2. So again, I can use some trig. So that means this is going to be, remembering this is 51 centimetres per second. So over here, that is going to be 51 sine 4.2, because I'm using this angle here. And this distance here is going to be 51 cos 4.2. So now I've just got to plug all of this information into my calculator. This value here is going to be that plus that. This value here is going to be that. Take away that. And that's just looking at the different arrows that we've got. Okay, I'm going to do those numbers and I'll be back in a minute. Okay, I'm back and I've done some calculations. I found that this length here is 48.4 centimetres per second, and I found that this length here is 43.7 centimetres per second. So already I can see that because these values aren't quite the same, our value is not going to be as close to 45 degrees in here. Let's have a look and see what it's going to be. So theta is going to equal tan to -1 opposite 48.4 divided by adjacent. Popping that into our calculator. Second tan 48.4 divided by, okay, and so we're getting 47.9 degrees. So that's going to be our angle in there, and our distance is going to be the square root of 48.4 squared plus 43.7 squared, close bracket, 65.2 centimetres per second. So our final answer, just make sure you can see, our final answer for our vector change in velocity red is going to be equal to 65.2 centimetres per second, and true bearing, so adding 90 to our 47, 137.9 degrees true. So just going back and comparing with our final, the last one. So even though we can see that they're not exactly the same, they are pretty similar. And that's not a bad job, considering the technology that we're using, and also the fact that we're making an assumption that it was a perfect collision, and by the looks of it, perhaps it wasn't quite. Well, I hope this all helped.